Kia ora Year 12. This is a very old calculus question, but a really nice one. It's a differentiation problem, and it's an optimisation question. So here it goes. It's question 10 from 2005, and we've given a cone with a cone inside it. So the cone has got a height of 15 centimetres, and the radius of the base is 9 centimetres. So we can think of that as our big cone, and then inside it we've got an upside down little cone. So here's, that's not right. Oh, yep, that's right. That's my big cone there. And this is 9, and this is 15. Now, inside it is this little cone peeking out here, like that. So the little cone has got a radius of r, and it's got a height of h. What we have to do is figure out how can we maximise the volume of that cone. So whenever I do an optimisation question, the very first thing I do is to think, what am I trying to maximise? Well, it's the volume of a cone, which is 1/3 pi r squared h. Now, when we look at that, it's got two variables, but we can't do anything with two variables. So we need to find a link between h and r. And once we've got that, we're going to substitute in for one of those, and then to optimise, we'll differentiate, set the derivative to 0, solve it, and then check that we've got a maximum. So the trick is to figure out how do I get that link between h and r. And there are three methods that usually will work. Similar triangles, Pythagoras, and trig. So the one that I'm going to use here is similar triangles. So that's your clue. Pause the video and try and get as far as you can using this diagram here to get a link between r and h. Okay, so here's my big triangle. That's 9 and that's 15. I think when you first look at this question, it's quite hard to see what to do because you tend to, well, I tend to focus on that triangle there, and it's not obvious if that's similar or not. But if we break it down further, we're given that the height of that cone is h, and so the height of this bit has got to be the leftover, 15 minus h. And once you start looking at this triangle in here, it's much easier to see that this little triangle and this big triangle are similar. Right? Remember, similar triangles have got the same angles. Well, we know they've both got a right angle. And we know that this angle here is going to equal this angle here. So this is 9 and this is 15. This is with r, the thing we're interested in. And this isn't h, but it's 15 minus h. So setting up the similar triangle relationship, and there are different ways to do this. I look at my big triangle and I go, well, this side divided by this side is 15 over 9. That ratio must be the same for this baby triangle. So we get 15 over 9 is equal to 15 minus h over r. Now, all we have to do now, and it really is all we have to do now, is rearrange this and get either r or h as the subject. So think about the smart way to do that. It's going to minimise work because sometimes that's what we want to do. If we get h equals blah blah, we're not going to have to go on and square it. If we get r equals blah blah blah, we'll have to square it. So I'm going to make h the subject. Simplifying here, we get 5/3 is equal to 15 minus h over r, giving me 5r over 3 equals 15 minus h. So h is equal to, let's see, 15 minus 5r on 3. I'm going to take this and sub it in. So v is equal to 1/3 pi r squared times 15 minus 5r on 3. I'll expand that out now and I get 5 pi r squared minus 5/9 pi r cubed. So, for maximum volume, dV by dr will equal 0. So dV by dr is 10 pi r minus 15 on 9, which is 5/3, so 5/3 pi r squared. We're going to set that equal to 0. So let's times everything through by 3. 30 pi r minus 5 pi r squared is this. I've got a common factor of pi r times 6 minus r equals 0. All right, so I get two solutions. I get r equals 0 or r is equal to 6. Now, intuitively, this is going to give me the minimum. But just to make sure everyone's good with doing a proper check for mins and maxes, I'm going to do it thoroughly. So the second derivative test is the easiest thing to do here. The second derivative here, we want to go back to this one, is 10 pi minus 10 over 3 pi r. And that equals 10 pi when r is 0, which is greater than 0. So we've got a minimum at r equals 0. And now we'll check when r equals 6, we're going to find that we've got a negative number. So that's 10 pi minus 60 on 3 pi, which is negative 10 pi, less than 0. So we've got a max. So maximum volume when the radius is equal to 6 centimetres. But we were asked to figure out what that maximum volume is. So we need to sub it in. So V is equal to 1/3 pi r squared h. What was h? H was 15 minus 5/3 r. So that's 30 over 3. So that works out to be 10. No, that works out to be 5. So height is 5 centimetres. And the radius is 6 centimetres. So the volume will be 1/3 pi times 6 squared times 5, which is 60 pi cubic centimetres, roughly equal to 188 point something. Let's check, 188.5 centimetres cubed. So there you go. It's a really, really nice optimization problem. I'm going to try and find a few more of those in the next couple of days. If you see any when you're revising and you'd like me to do a particular one, just send me an email. Thanks for watching.